就是让这个最小的就让这个还是最小的I mainly do I mainly do like practice.
Okay, welcome back, everybody. Let's go ahead and get started. A couple of sort of bookkeeping announcement type thing first. First thing is in case you hadn't seen it, office hours are posted on the front page. I have office hours every Wednesday at 3. Ramon, I think you're Mondays at 3. So there's remember homework coming up due Tuesday. I remember correctly on the schedule. And that's due 1 minute before midnight. Which reminded me I need to put a place you can upload it on Canvas, but that'll be up there shortly. And so you just upload a single Python Jupyter notebook to Canvas. And just a reminder what we're expecting. So you've got these couple of problems, which are math problems, right? And those should be typed up in Markdown, or you use $signs. You can put LaTeX to get math notation. So type up the math. It's not a lot of math notation you need, just need like a set A, B, whatever, and subsets and things like that. You don't need a ton of equations or anything for the math. And then of course in problems 3 and 4, you got to do a little bit of Python coding to solve those. And so those should be, code blocks that run. The whole notebook should be kind of self-contained. If you have any questions about any of that, let me know. And just a reminder, there's some example Jupyter notebooks. If you don't have much experience with Jupyter, on the front page, I think linked on the front page, you can kind of take as examples, one of which has lots of math notation you could copy from. But anyway, if you have any trouble with that, let us know. The other announcement I wanted to make after people were asking yesterday during my office hours, is we, or I can speak for myself, I think there's also a whole Ramon, are available after class. So there's the 2 days of office hours are Monday, Wednesday, but Tuesday, Thursday, you can imagine after class is like bonus office hours for the, we'll hang around however long, maybe not infinitely long, but we can hang around for a while after class to answer questions. So always take that into account and feel free to come up to us after class. So we really have all the days except for Fridays covered for in-person help. And then if you have questions, remind everyone there is Piazza. I don't think anyone's posted to Piazza yet. I checked at least yesterday. And if you have any questions and you don't have this available at the moment, you're working on your homework at 3 in the morning, post to Piazza a question and we'll answer it, or also feel free to chime in to your fellow students' questions if you think you can contribute to the whole class, and you're confident in that. I encourage everyone to discuss things on Piazza. I think that was the announcements. Any questions on course logistics, or any questions about the homework assignment specifically, or anything? Okay. Yeah. Okay, so today our goal is to finish differentiable manifolds. So we've covered in the past couple of lectures, we covered manifolds, and the concept of differentiable manifolds. I'll review that, both those definitions briefly here at the beginning. And then our goal is to finish manifolds. One thing we have to talk about are tangent spaces, tangent vectors and tangent spaces. And then to get started on the next section, which will be section 3 of the notes about Riemannian geometry. And this is where torus curves, geodesic curves, we get the distance metric on our manifold. Okay, that's kind of the high level thing. We'll go into some details here, obviously. So yeah, let me bring up the notes so I don't. For some reason, this computer's moving super slow to just confuse you. So okay, here we go. Right, so I forgot to bring my own chalk. Thankfully, there is a piece of chalk here. Otherwise, this would be a very weird lecture. Anyway, okay, so let's just review really quickly what is a manifold. And again, if you look in the notes, section 2 is just about manifolds. When we say manifold, you could say topological manifold. So this is just a topology definition at first, nothing about differentiability. And so this you could call a C0. C0, remember, means zero different derivatives necessarily, but C means continuous, so it just means it's a continuous manifold, or topological manifold. And this had to satisfy 3 properties. The first one was its Hausdorff. I should say, okay, I need a name for this thing. Let's call this a manifold. I'll think with the Hausdorff space M. Okay, so Hausdorff, just remember, is a topological space. I think M is a topological space. And any 2 points, let me call it P and Q. P and Q that are in M can be separated by open sets. So an open set, let's call it U, an open set V contained in M, that U contains P, V contains Q, and they're disjoint. They don't overlap at all. Okay, so that's what we mean by Hausdorff. And Amann had a very nice, it's not in the notes, and we'll make it come to that later, but it's not in the notes, but had a very nice kind of intuition for why we care about Hausdorff property. And that is that our usual notion of convergence of sequences, you can think also as limits, requires this Hausdorff property. Because remember, if you have a sequence, what you want to have happen is that any little open subset, small open subset around the point it converges to, you should have that the sequence eventually lands in that open set and never escapes. So for all, past some point in time, if time is the, when the sequence is evolving, you should be stuck in a small open set around the point it's going to converge to. And usually with Euclidean things, we talk about an epsilon, any epsilon ball about the point it converges to. So the point was that Hausdorff, this separation axiom is really necessary for that definition of convergence to hold. So I'm going to point out that, of course, when you do calculus, right, you talk about sequences and sequences converging, and we define derivatives as limits, and none of that would work if we didn't have this property. So our goal is going to be calculus. Of course, manifold topology doesn't have calculus in it yet, but we wouldn't be able to do the differentiability and the calculus stuff without this property. That's one of the reasons, not the only reason, but one of the reasons this Hausdorff property is pretty critical. The next property is that it has a countable basis. And remember, a basis is just a kind of core set of open sets that you can build other open sets with. won't go through the whole definition again, but it's like the open balls in Euclidean space, or the open intervals if you're just one-dimensional real line. And so they're the building blocks to make up all the open sets. Countable, remember, just means you can count them. You might count to infinity, that's okay, but you have to be doing integers like 1, 2, 3, 4, possibly up to infinity. That's how you can enumerate all the elements of the basis that way. You could not have a basis element for every real number, because the real numbers you can't count and put them in correspondence with the integers. It's a larger infinity than the integers. So this is somewhat of a technicality. There's some reasons to have it, but you can kind of think it like you can't have your topology be too big. You have a sort of a limit on the kind of pieces you can put together to make up your manifold. And just again, point out that this is our usual spaces we're familiar with. Euclidean space, Rn, vector spaces have countable basis because, as Aman pointed out, I'll just remind everybody from last time, you can take the open balls that have just rational numbers as their centers and rational radii, and the rational numbers are countable because it's like looking at integer divided by integer. You can count those things. And so Euclidean space has a countable basis. You just stick to rational numbers. You can cover the whole space and satisfy all the basis properties. So that's something that Euclidean space has. We're adopting on our manifolds also. And then the third thing, and this is really the key thing, if you never remember these first two properties, you'll be all right. Just remember the third property. It's the key ingredient that we think of when we talk about manifolds. It's the main intuitive thing that you need to be able to remember. And that is that at any point on our manifold, say P on M, there exists an open set containing P and homeomorphic to Rn for some n. Okay. And again, Rn is just the space of n-dimensional real vectors. There's some n, so some dimensional vector space, Euclidean space, where there's a neighborhood, sorry, I should say open set containing P. If you ever hear me say neighborhood, neighborhood of a point means an open set containing that point. Okay, like this is use a neighborhood of P here. It's an open set containing P. Yeah, so this, if I can just say this in one phrase, I'd say every then M is locally homeomorphic to Euclidean space, right? That's the way we said that. Locally homeomorphic means that for every point P, there's a local open set containing that point P that's homeomorphic. And remember, homeomorphic is topologically equivalent. It's a bijection from this open set to all of Rn, bijectively equivalent and sets, and it's continuous, and its inverse is continuous. And remember, topologically, that means there's no topological distinction. All the topological properties of Rn are the same topological properties you can get for this neighborhood of P. Okay, and again, one last kind of intuition there is that we think the most common example I like to think of is you're on the surface of the Earth, you're walking around outside, and you feel like you're walking on R2, just on a plane. If we are small enough, you don't see any curvature. Of course, curvature is a thing we haven't gotten to yet, and it has to do with geometry, not topology. But for all intents and purposes, we are walking on a plane because we're very, very local to the large manifold we're all standing on right now, or sitting on now. Okay, so that's a topological manifold, which we can call a C0 manifold, a continuous manifold. Any questions on sort of that? Yes.
So to clarify, are you saying that the open set is homeomorphic?
Yes, so this open set U, I'll call it, containing P is in this open set U, that's the neighborhood, like if this is a manifold. M, and got the Hausdorff property, I can reuse this P and this U as the neighborhood of P. That open set, I'll shade it in here, but there has to exist some open set around here. It could be larger or smaller depending on your manifold, but that whole open set is homeomorphic to Rn. And yeah, one thing that maybe trips people up a little bit is you're like, well, okay, this is like a nice, the way I'm drawing it, but let's take Euclidean space as an example. It's homeomorphic to itself, so it's globally a homeomorphism, but you can also think locally. If I just took an open ball, you know, bounded open ball, I can make that homeomorphic to all of Rn. So this notion of boundedness is actually not a topological property. It's a metric property because obviously the metric bounds you in a ball, but all of Euclidean space is not bounded in terms of distances. But in terms of topology, you just think of open or functions that have asymptotes. So like if I have something like this, which is kind of like a nice continuous function that's also invertible, I can take an open interval to the whole real line, or vice versa if I invert it. So this notion of like being a local neighborhood, if we do have the metric and it's bounded, a little local neighborhood being equivalent to all of Rn, it's actually, I could have said this same definition that there's an open set equivalent to a ball in Euclidean space, because a ball in Euclidean space is equivalent to all of Rn. So don't get kind of tripped up about, okay, I've got a little local thing and it's equivalent to all of Rn, because that is really okay. It's kind of the same. Okay. So yeah, so that's a topological manifold. And then the thing we added last time was a notion of differentiability. And here we might say CK manifold, a CK differentiable or CK manifold, where K is an integer. K is in a positive integer, so it's integers greater than 0. Actually, I should take that back. It's okay for K to be infinite, so you can have a C infinite manifold. That's what when we say the phrase smooth. Smooth typically in math means that there's an infinite number of derivatives that exist. So CK means there's K derivatives. You can take K derivatives of a function if you have a CK function, and those derivatives are continuous. When you take the first derivative, it's a continuous function. You take a second derivative, it's a continuous function, up to the Kth derivative that you take. Okay, so because again, this C means continuous. Right, so differentiable manifold, the sort of piece we're adding here is that it has, I'm making it number 4 here, so adding it to the 3 rules that we already have. So CK manifold has to already be a C0 manifold. It has to satisfy the topological properties, but it also has to have a maximal CK atlas. Okay, and this maximal atlas, just to remind everyone, was that you have charts on your manifold. I'm not going to write the whole definition there. I'm just going to kind of quickly review it because it's just supposed to be a review here. You have these local charts, and I write X and Y and things like that as the actual mappings from these charts, and a chart is just an open set. I should probably draw this It looks open. You take an open set U and you map it to Euclidean space or N, and it maps down here. And then if I draw, there's a picture of this in the notes, I draw a little grid here. And this is the image of U under X. So X is a function from U to some subset of R and M. This is, I should say, this is a chart we're talking about here. And I can think of these, the reason we call it a chart is you think about these grid lines, like when you have a map of, like the globe of the Earth, and you have like longitude and latitude line. I can draw that, I can take the Earth and kind of project it down to a nice rectilinear map with grid lines. But I can also think of these grid lines, because X is going to be homeomorphism. So I can invert it. I can think of these grid lines as also living up here on the manifold M. Okay, so the idea is that a chart, we call it a chart because we think of an atlas, also we think of maps. So a chart, you think of like, okay, everyone here uses Google Maps and things like that now, but back before Google Maps, there's things called atlases that were paper books. Don't know if I have to explain this if people know this or not. So an atlas would be a book, and every page would be a part of a map. Like you think of tiling a map, right? And each little page would be like a chart. Okay, so this is why it's called charts and atlases. So the charts are like the pages of your atlas, and they just show you a little local piece of the manifold. But the atlas puts together all those pieces. It's the collection of all the charts. Okay. Now, to be an atlas, you can't just throw in charts willy-nilly. The charts have to agree with each other when they overlap, and that's this notion of compatibility of charts. Now, if I have another chart Y going from another open set also to Rn. Another open set V, and it has another chart Y down to Rn. It maps to another open set of Rn, let's say. Then in the intersection, they intersect in this little wedge. I need this to look like a coordinate change, like we're used to in calculus. I can change coordinates. If you give me a coordinate system on, just R2 or whatever, like Cartesian coordinates or polar coordinates, I can do a change of coordinates between those two sets of coordinates. And that's what we're talking about when we talk about compatibility of two charts. Now, the trick is that the change in coordinates is all down here in Rn. We have to go up to the manifold and then back down to the other chart. But in the end, the composition is just a function from Rn to Rn. So going this way, I go X inverse and then Y, composed with Y. So let me write that over here. I first go X inverse up to the manifold, and then I compose that with the function Y. And that gives me a mapping this way. X inverse composed with Y is a mapping from this Rn to this Rn. And then, of course, I can go back the other way, which is really just the inverse mapping of this, because these two things are homeomorphisms. So you compose homeomorphisms, you get a homeomorphism in the intersection, where they both have the same kind of outputs there. And so I can also go the other direction. This is defined on X of U. Wait. Let's see, if I'm going that way, it's defined on X of U intersect V. That's the domain. If I go the other way, X composed with Y inverse, it's this intersection is, again, the U intersect V pushed through Y is the domain. So the domain there is Y of U intersect V. Okay. So what do I need? I need both of these functions. They're already homeomorphisms just because X and Y are homomorphic. I can invert them, everything's a homomorphism. But what I need them to be to get this differentiability is I need these are now functions from a subset of Rn to Rn. And now I can say, I know what differentiability in Rn is. I need these to be CK functions. And really they're CK functions of these open sets that between these two open sets in Rn. Okay, so they're K times differentiable functions. And they're also invertible, and they're going the other way, going both ways are CK differentiable mappings. We call that a CK diffeomorphism. And diffeomorphism, when we're talking calculus, means that these two spaces, these little open sets right here, are the same in terms of calculus. They have the same topology, but they also have the same derivative and integral properties as well. Any kind of calculus I do in one will be the same as I did the calculus over there. And another way of thinking of it, again, keep in mind, is just think of change variables, change of coordinates in calculus. If you change coordinates, you can just write an integral. You get the same number. You change coordinates and do the integral in a different set of coordinates. You'll get the same output, right? That's the equivalence in terms of calculus. Okay. So long story short, this turned into a longer review than I was expecting, but that's okay. The maximal atlas, what that means is that if you first have put down enough charts to cover your entire manifold, you then have to toss in all of the charts that are possible that are compatible to those sets of charts. And if you can't toss any more charts in there that are compatible, you've got a maximal atlas. Okay, so you have to include all the charts that you could possibly throw in there that are all compatible to get a maximal atlas. Any questions? That's, I think, my review of just what's a manifold, what's a differentiable manifold. Yeah.
What do we do in the case where there is no overlap amongst any base? Like,
Yeah, good question. Yeah, that's a great question. If U and V didn't overlap, then they're compatible. So so if U and V don't overlap, it's by kind of like a what do you call it, vacuously true that this thing works, because the intersection is just the null set, and so it's vacuously differentiable in the null set. So any non-overlapping U and V are compatible, but they may not be in the same maximal atlas, because there may be things that are compatible to the U, that, let's say, this XU chart, that do overlap with another chart, but aren't compatible with it. So everything has to be mutually like compatible with each other. All the charts you throw in there had to be compatible to all the other charts. And so you can think of, like, if I had chart here, chart there, maybe this guy is compatible to this, but this guy is not compatible to that, and then it would break, and you'd have to toss one of them out to keep everything compatible. So if they don't overlap, you have nothing to check. You don't have to worry about charts that overlap to check them, but they all kind of have to work together if you put them all together into the same atlas. Yeah, that's a great question. Any other questions? Just a fun trivia fact, which again, you know, is more like a interesting thing to think about, but isn't a thing that you need to know for the class necessarily. It's a fun, like, quirk of mathematics. I think it's in the notes actually. Let's see, I think it's example like 2.4 maybe. Example, yes, 2.4. I'll just summarize it. Hand wavy summarize it. But if you look at the real line, it's a manifold. It is all these things. It's locally homomorphic to it's globally homomorphic to itself. So any Euclidean space knows a manifold. It is, of course, you could take a chart, which is just the identity function of x equals x, right? Or y equals, or f of x equals x. You just have an identity function as a chart. And that chart covers the whole manifold. And this is the thing with maximal atlases, you're done. You don't need to do any more charts. If you get a chart that covers the whole manifold, or you get a set of charts that cover the whole manifold, then you just throw up your hands and say, that is a atlas. And I'm going to say my manifold is then any other charts that fit into that compatible with those charts I've defined. And you don't actually have to specify all those charts, because any set of charts that cover the manifold, this is a theorem in geometry or manifold geometry, is that there's a unique maximal atlas. So you don't have to define, it's kind of like defining the basis elements. You don't define all the open sets, you just define the basis. Same thing here, you define enough charts to cover your manifold, and then you say, I'm done. Every other compatible chart is included in my atlas, my maximal atlas. So the trivia fact is the real line, I can actually give it multiple differentiable structures that are not compatible to each other. So I can give it multiple maximal atlases that don't agree with each other. So take the real line like I just mentioned and take the identity function. That's clearly a chart that covers the whole manifold. That gives me a differentiable structure on the real line. Now take the function x cubed as a chart. At the point 0, where it has 0 derivative, it's not compatible with the identity function chart. Okay, and because you can't get a diffeomorphism where there's a 0 derivative, because you can't invert the derivative there. And so x cubed is a completely different chart. And again, it has its own maximal atlas, but it's not compatible to this maximal atlas, the usual maximal atlas. Although you can write down a diffeomorphism of manifolds between those two manifolds with those two different differentiable structures. They're actually diffeomorphic to each other in terms of the definition on manifolds, not in the compatibility of charts. And so, so you say that's okay. These manifolds are the same up to diffeomorphism. And it turns out, this is kind of a trivia fact, is that is the case for all possible Euclidean spaces Rn, except for one. R4 has more than one differentiable structure that are actually not diffeomorphic to each other. So this very weird thing, and it's hard to prove, it's a famous result. R4, four-dimensional Euclidean space, has multiple different differentiable structures that are completely not diffeomorphic to each other. And it's the only Euclidean space that you can put these weird differentiable structures on. But I'm not aware of any actual practical use to that. It's just fun trivia to that. Okay, but that's a side note that you don't need to worry about. Any questions? Okay. Yes, a question up. Okay. So today, to finish up differentiable manifolds, the last thing we have to talk about is tangent vectors and tangent spaces. And I think everyone, again, has an intuition for what a tangent vector is. You're familiar with curves and tangents to curves, and maybe surfaces and tangents and tangent planes to surfaces. So let's talk about that for a second. And then basically all we're going to do is, like everything else in the class, like continuous functions or what have you, we're just going to abstract it to the more general case of this differentiable manifolds. Okay. So let's start with curves. We're all familiar with, if I have a curve, let's say gamma, which is, let's say gamma of t, which is a function from some interval a, b in the real line to, let's just do R2 for now. We also know about space curves, and R3 is fine too. What do we mean by a tangent at a point? So we just mean the velocity of this curve. And so that really is just d gamma dt. Let me call this, give the name, this vector v. I'll say is d gamma dt. Evaluate at t equals some value, let's say t naught here. Okay. Yeah, we know that the velocity vector to a curve, it's just kind of the if I'm in R2, this is, by the way, yeah, I should mention this is always going to be just a vector in R2. And this v, it really means I'm moving along this curve, and my instantaneous velocity, it's both the speed is like the length of v. If I'm actually have some units here like meters, right? And my time is in seconds, I'd say the length of this would be in meters per second, like that's the speed. But the direction of this vector is also the direction I'm moving at that instant in time, right? That's what we know about velocities of curves. That's all pretty standard. And then this word tangent, of course, you typically think of tangent, meaning that if I kind of think of this as a, you know, a line that this vector is moving in, that this vector is kind of defining, this curve really touches it at that one point. This is kind of this notion of tangent. I mean, obviously, okay, I can, you know, be really curvy and touch at many points this line, but in terms of like around a little epsilon ball here, I'm really just kind of touching this curve at one point. The curve is touching that line at one point. So that's what we mean geometrically when we say tangent. Okay, so that's kind of the thing to remember. Now, if I do this for surfaces, I'll just do the spheres, another great example. The two sphere. Again, think of the Earth and a unit sphere, let's say radius 1, and I look at the North Pole, the top point here, and if this is radius 1, then this point is the point 0, 0, 1, if this is my z-axis, if you will. And we know that if I were to take the z equals 1 plane, the constant z plane, that I would have a 2D plane that touches the sphere at that one point at the North Pole, just sits right there on top of it. And it's, again, that's the word tangent, right? It just hits it at one point. And this is sort of the tangent plane now, because we're a two-dimensional thing. We're a tangent plane to the sphere, okay? One thing to think about here is these tangent vectors. The tangent, the tangent space here would be all possible vectors that are in this line, if you will, right? And here I've got kind of a vector space of 2 dimensions where any vector here in this plane that's, you know, spans this plane, any vector there is going to just touch kind of the base point, right? So one way to think of this geometrically, again, at this concept of tangent, is that, okay, if I have a point on a nice smooth surface or smooth curve or what have you, but I wanted to approximate it with just a single vector space. What is the best vector space to do that with? Well, it's the space that's just tangent at that point, up to first order meaning up to first derivatives. It's what that, if you did a Taylor series of some kind of function that gave you the sphere, you would get this plane as the up to first order approximation of the sphere. Okay. Then the final thing I'll just make in terms of our intuition, things we already know, is if I think of curves again, but now restrict to be curves that are on the sphere. Okay, so think of like bird migration paths on the Earth, right? And I'm going to have a curve that passes through the North Pole here, 0, 0, 1. So any curve, it's got to stick to the sphere and it's got to pass through 0, 0, 1. If I look at the velocity of that curve as the usual definition of velocity of the space curve, the 3D space curve, now I'm a vector in R3, but that vector in R3 is going to be in this tangent space, because it has to touch the curve again at one point. And hopefully you can convince yourself that that's going to mean it's constrained to this space, this 2D space that sits down at one point and is the plane z equals 1. E equals 1. X and Y can be anything you want, but the z coordinate is constant at 1. Okay. So that's the concept to keep in mind, this tangent plane to the North Pole of the sphere. That's what we want to define for general manifolds of arbitrary dimension. And I should mention, notice our manifolds, differentiable manifolds we have defined here, they don't have to be living inside of some larger Euclidean space. So the sphere here, S2, lives inside of R3, but an arbitrary differentiable manifold has no connection necessarily to a Euclidean space that it lives inside of, right? That we don't have to have a embedding into Euclidean space. So this concept of a tangent space, where in the sphere case, because we're embedded in R3, this tangent plane leaves the space of the sphere. It's somehow separate from the sphere, which is that's okay, but it also lives in the embedding space. But when we have a abstract or just general manifold, we won't have an embedding space for this tangent space to live in, but it's still well defined. Okay, any questions about this? Again, it's stuff that I think everyone knows at some level, and you can imagine at least, like, we're all used to curves and taking velocity of curves, and you can imagine those curves living on some surface and restricting ourselves to that surface. And now we want to do this for in more general case, but keep this picture in mind. Okay, great. But how do we do this? How do we define tangent vectors when we don't have, again, a sort of ambient Euclidean space that we're traveling around in? So as you can imagine, from what we've seen over there, now I'm going to have a manifold M, just like on the sphere, and I'm going to start with curves, gamma, or a curve, let's say gamma on this manifold, and I want to say, what is the velocity of this curve? So let's first write down what is gamma. Gamma, I'm going to, you can again give it some arbitrary interval a, b, or the whole real line if you want, but for our purposes, I just need little short guys that are some small interval of 0. But I can find other curves, but this will be useful for the purposes of what we're doing here. And so you can think of it as it's a mapping from some interval, and again, I'm just going to use this as for convenience, minus epsilon to epsilon, that outputs points on the manifold. Yeah. Now gamma, I should have mentioned this here. Obviously, I needed gamma over there. By the way, it would be a C1 because I took a first derivative of it, right? So here I'm also going to need gamma to be C1. I think we call it mappings of functions. I need it to be a C1 mapping. And just to remind everyone, what does it mean to be a C1 mapping of manifolds? Again, this was last lecture. The idea is that here I'm going from the manifold, which is the open interval minus epsilon to epsilon, gamma then takes me to the manifold M. And for it to be C1, it means that I'm going to forget about, this is a manifold technically, right? Minus epsilon to epsilon. So I would technically need a mapping to a chart, but that's the identity function because it's a manifold. The chart is just the identity. So I'm just going to put the chart here. So this is here. And again, what I need is that there is a chart. Let's call it little x. Such that when I map this open set that x is defined on, down here, I'll get also the image of this gamma output down here. And I need the composition all the way through from Euclidean space to Euclidean space to be C1. Okay? Because in and of itself, I can't define things to be differentiable on the manifold. They always have to go through a chart down to Euclidean space. Okay, yeah, technically there's also a chart here that if this were, I would do this, but it's just the identity, so I can kind of just erase it, honestly. So let me write this out in notation. What do I mean here? I've got a chart X. I'm going to take gamma composed with X. Gamma goes from minus epsilon to M. I'll write this out. X goes from M to Rn. I should say it really goes only in this open subset of M. It's only defining U, but that's a subset of M. And so again, this is only if gamma intersects this chart does this matter. This has to hold for any chart where I can intersect the chart with gamma. The composition of these two things, so take gamma, compose it with X. Now I'm going to go from minus epsilon to M and then M to R. N, so this composition is from minus epsilon to Rn. And now, of course, this is just a subset of a real line. Now I've just got a curve in Rn. Sorry, I'm messed up the camera for zoomers. Now I've just got a curve, an interval, open interval from Rn. That's just a usual space curve or n-dimensional curve. And now I can take the derivative of this function. So for it to be C1, this composition has to be C1. Okay. Okay, so that's just a special case of the definition being a C1 mapping between manifolds that Aman covered last time. A specific example being curves, or specifically can be CK curves. Okay. So yeah, so that's our setup. Gamma is a differential curve on this manifold. At least first order differential may have higher derivatives, but we just need the first derivative. And as you can imagine, we're going to define at a point a tangent vector to be just that derivative. Okay, but it's a little bit indirect because if I take the derivative of this thing, which I can do because it's a Euclidean thing that I know how to take derivatives of, I'm going to define a velocity down here, right? Because that's where the space curve, the Rn embedded curve is down here in Rn. So but I'm going to define it up here on the manifold, not down here on the chart output. Okay, so I have to do this in a somewhat roundabout way in order to do it up here. Let me make one further point to kind of drive that home. If I let it just live down there and say I'm done, this is my tangent vector, and it corresponds to a point up here, so I'll just say that that's my tangent vector. Well, what happens if I change the charts? I get a different chart. I get a completely different space I'm mapping to. It's Rn, but it's a different copy of Rn for a different chart, and I get a different tangent vector, and then I've got just this big mess. So I really need it to be a way to define the tangent vector up here that is independent of which chart I pick, okay? And this is kind of the game we play when we start trying to define things that live sort of intrinsically on the manifold. They shouldn't depend on which chart I picked, how I map it to Euclidean space. It should live in and of itself up here on the manifold, okay? I always have to go to Euclidean space if I need to do some kind of calculations, but I want to be independent of that problem. Yeah.
And it's like we already have a function that goes back to the manifold from that image. Like, why is it necessary, important to live in the manifold itself?
Yeah, so you mean like we have a mapping. If I just were to invert this because it's a homeomorphism, I can always go back up to the manifold. That's right. But that lets me take any point and put it back up here. But this tangent vector is not a point in the space. It's technically like it's another copy of Rn, if you will, that has origin at this base point, if you will, in the tangent space to this Rn. And so there's no way to bring this vector back up here through X inverse. It's not the X is sorry, this, let me call this well, let's call this vector is dt of X composed with gamma. And again, let's say I'm going to evaluate this at 0 t. That's why I made it at minus epsilon to epsilon. So this is at t equals 0. If we say that gamma of 0 is this point p, let's say we're interested in is this point p in our manifold. The derivative as I pass through that point p, again of this gamma composed with X, like I said, is a vector down here, but that vector is not a valid input to X inverse is the point. Yeah. Okay. Yeah, and so we'll see in a minute here, we can square this circle, if you will, and make things work out nicely. We just have to do it a little bit indirectly. Because one thing I also will see in a minute, it's not just the choice of chart that matters. We'll see it's also the choice of gamma that matters here. I want this actually, this notion of a vector to not depend on necessarily the specific gamma function, curve I actually chose. So I will go through that in a minute. And why that's important. Okay. So yeah, so what are we gonna do? We're gonna define, again, a tangent vector should look like the speed, or sorry, not the speed, but the velocity of a curve on the manifold M. And we just need to make that make sense somehow. So another way to think of a speed, or I keep saying speed, a velocity of a curve is you can think of it as a directional derivative operator. Okay, so it's a you can think of it not as a geometric thing with this property of tangential property we talked about, but as an algebraically as an operator that all it does is it takes functions and it computes their derivative in that direction. You remember from calculus directional derivatives, let's write it down. In calculus, and I'm going to use this notation. So V is going to be again a vector. In this case, we'll just say I'm just going to work in Euclidean space for now and Rn. And F is going to be a differentiable function from Rn to R. Okay, it's going to be F has to be at least C1 again. And I can take the derivative of F in the V direction, right? How do I do that? I'm going to take this notation V F. This is weird notation if you haven't seen it before, and you may not have, it's not common necessarily in calculus, but you can use the manifolds all the time. Is again, I'm thinking of V, again, not as this geometric thing, but as an operator that I can act on a function with. And so I'm going to act on this function F by taking its directional derivative, and I'm going to do this at a point, let's say X, where V is defined. And what this means is I'm going to say the usual derivative thing is I take a limit as epsilon goes to 0 of f of x plus epsilon v minus f of x divided by epsilon. That's your directional derivative definition. And again, the picture I have in mind is that I've got a point, I guess in this case, X, let me call it P, just B, because that's my coordinate system. We've got this point P, at P, I take the vector V, and this says just move a little bit along this vector up here and take the difference from here to the base point and just shrink that difference as epsilon goes. And so I'm taking a derivative just along this one univariate direction in Rn of really an n-dimensional function. I'm just kind of evaluating it only in one dimension. And the directional derivative says, what's the derivative of that function if I just restrict it to that one dimension? And travel at the speed relative to the magnitude of v, of course, here. Okay, so keep this notation in mind. This is basically just concatenation. So if you think of like a matrix as an operator acting on a vector, you just write it as a concatenation. Same thing here. This is just an operator acting on this function, and that's the way we'll write this is when we have directional derivatives. Okay. So notice this is just another way to think of vectors in Euclidean space. I can think of them as velocities of curves. And I can also think of them as operators that act on differentiable functions, and they're the directional derivative operators. Okay. And now we're going to take kind of both of those ways of thinking about tangent vectors in Euclidean space and define what we mean by tangent vectors on general differentiable manifolds. Okay. Right. So I'm going to move forward here. I'll move, but keep that stuff up. Okay, so I'll just redraw that picture I had over there, a manifold M and my C1 differentiable curve gamma, and a point P. The point P again is going to be at time equals 0 on gamma, so I'm going to have gamma defined at least from minus epsilon to epsilon. I'll just anchor, or I'll just name that point at time 0 to be P. That's what we're going to talk about the derivative for velocity V of that curve. And again, in Euclidean space back over here, V is just ddt gamma. But I can't define ddt gamma. I can define ddt gamma composed of x, because that gets you back to Euclidean space, but as of yet, I can't talk about what I even mean by ddt of gamma. Now, what I can do is when we talk about directional derivatives over here, I can define this. I'm going to say for any f, which is a C1 function from M to R. Okay, so just pick any differential function you want that takes inputs on M and outputs real numbers. I'm going to define this operator, evaluate it at P, to mean the following. It means I'm going to now take a ddt derivative of, sorry, let me make sure I get this right. F composed with gamma, like so, evaluate it at T equals 0. Okay. And if this, I define V to be now defined to be the derivative. What I mean by the derivative of gamma, I should say at T equals 0. Now, this is an object that, I mean, I'm defining this. We don't have, again, calculus yet because I need Euclidean space to talk about what is ddt, but I'm going to define this is what I mean by the derivative of a curve that has outgrown the manifold, is that it will act like a directional derivative. So that if I compose the curve with f, now notice, let me to make this clear, let me just talk about what is this gamma composed with f. Remember, gamma goes from minus epsilon to m, and f goes from m to r. So you compose them, and you get minus epsilon to epsilon r. And what are we doing here? So f is defined on all of m. And just like in the directional derivative example over there in Rn, I'm evaluating f only along the curve gamma. You can kind of think of gamma, wrong way, and followed by f is like I take the t from minus epsilon to epsilon, and I evaluate what is f as I travel along this curve, and I'll get a one-dimensional function over t, and this is a real number to real numbers. One, like I said, one-dimensional function, I can take a derivative of that. So that's how I can do this ddt business. Okay, and evaluate as you hit t equals 0. Evaluate what's the derivative of that curve at that point. And that is a well-defined way to say that's the directional derivative at the point P in the V direction, where V is what we're thinking of as the tangent vector. We draw a picture like this. Again, it's this very abstract thing that I have to say that this will hold for any function you give me. I can say this is what I mean by tangent vector, is the thing that acts like a directional derivative here. Okay. Last thing to point out is that, like when I mentioned that we would like not to depend. So notice I don't depend on a chart here. There's no charts. I also would like it to be the case that I don't really. I need to be careful that the V here doesn't need to be associated with a specific gamma, because we know curves, if I think about Euclidean space, can have the same velocity. So I could have a bunch of curves that have the same velocity, just like in Euclidean space. And what do I mean by that? Now that if I do this composition, I have, let's say, gamma 1 and gamma 2 here. I could do this composition, and I'll write it all out again. ddt f composed with gamma 1, evaluated at t equals 0, might be the same number I would get if I composed f with gamma two and evaluate it at equals 0. So I just did the, again, composition to get one-dimensional functions for gamma 1, and I did the same process for gamma 2. And I end up with the same number when I take their first derivatives, and it's 0. If this holds for all f again, right here, then we'll just say gamma 1 and gamma 2 are equivalent. If this, this holds for all f, then we'll declare gamma 1 is equivalent to gamma 2 for purposes of what do we mean by tangent vectors at P. And then really the V is this whole equivalence class of curves. It's not just one curve, it's all the curves that have the same derivatives as you pass through P. So they all have the same derivatives for any possible choice of f. And just think in Euclidean space, of course, I can have two curves that have the same velocity at a point, and then we would call them equivalent curves in this definition. And you can think of that equivalence class of all curves that have that property to be the velocity vector. Okay, so there's this technicality that the directional derivatives may have multiple curves that need the same directional derivative operator, and I just have to include them all together in a big equivalence class and call that equivalence class the vector. Okay. Any questions about, again, it's a little bit of a roundabout way, but it really is thinking of tangent vectors the same way we think of them in Euclidean space as velocities of curves, but also as directional derivative operators. And this is our very first example of we are now doing calculus of manifolds. We're doing derivatives. We're doing directional derivatives. You need to have this notion of a tangent vector to get into calculus, and that's what we've done so far. Okay. I hand waved over this argument, but just to explain where there's more under the hood, notice that I have to be able to show that this is a whole well-defined thing. Okay, so you have to show that this is an equivalence relationship, and you can do this, it's pretty straightforward. Remember, an equivalence relationship means that it's reflexive, so gamma is equivalent to itself, gamma. It's symmetric, meaning gamma 1 is equivalent to gamma 2 is the same thing as gamma 2 is equivalent to gamma 1, and it's transitive. So we have gamma 1 equivalent to gamma 2 equivalent to gamma 1 or 3, then gamma 1 is equivalent to gamma 3. So reflexive, symmetric, transitive. I didn't prove all that, but it's fairly straightforward to prove that. You have an equivalence relationship between curves. And yeah, then that all works. Okay, so that's the technical definition of tangent vectors. And again, you don't have to remember the technical definition so much as you just need to understand the intuition. And so that's where, again, I'll point you to this picture that we think of with curves and surfaces and velocities of curves on surfaces, and the space of all vectors that could be written as velocities of curves through a point. So yeah, so this, back over here on the general case, these V's, these tangent vectors at a point P will make up, just like the sphere case where you have a plane, you take all possible curves, all gammas through P, and you'll get a whole vector space. Okay, and that vector space is called the tangent space at P. So the tangent space at P, just the notation for that in the note you'll see is TPM. So it's just tangent space at the point P of the manifold M. And again, I'm not proving this, but you can kind of guess that this would be the case, just like the sphere. If you have an n-dimensional manifold, this TPM will be an n-dimensional vector space. It'll have the same dimension as a vector space as the manifold has. Okay. Again, not that hard to prove, but we're not here to do proofs for the whole semester, so we're going to skip all the proving things. Okay. Great. Any questions about tangent vectors? We'll, in the next lecture or so, we're gonna use tangent vectors. We're gonna see them and get more familiar with them as we go, but right now, this is just kind of the definition of things. Okay, right, and so now we can do calculus. We've got derivatives. And I'm gonna do one more. In the last 8 minutes, one more calculus thing. And that is, we've got essentially derivatives now between of curves, and you can think of curves again as smooth mappings from basically R1 to some manifold M. So we know how to take derivatives of those types of mappings. Now let's think about what if I have two manifolds M, another manifold N, and they can have different dimensions, even though I've both drawn those two-dimensional blobs sort of here, but M and N have some, dimensions, little n, let's say. And now I have a differentiable mapping F that goes from N to N. This is, again, going to be a C1 mapping. At least it could be C higher than 1, but at least one dimension, one derivative. And again, derivative means that if I went down to charts and did the composition from the chart back up to manifolds, then through F, and then back down to the chart, I would get Euclidean to Euclidean mapping, and that would have to be C1 derivative differentiable. That's what we mean by C1 again. If I push things down to the charts, then that whole composition will be differentiable. But now what do I mean by a derivative of this mapping? Okay, so how do I take derivatives of mappings from a general differentiable manifold to another differentiable manifold? Sorry, I should mention M and N, of course, from now on will always be differentiable manifolds. Not just, obviously, they have to be differentiable manifolds now. So it helps for us to review the case where you have Rm, Rn, for better N. Okay. If M is Rm and N was Rn, we would be doing multivariate calculus. This mapping would have a derivative, which we know is called the, what is it? We have a mapping, multivariate mapping, and you take its derivative. What do we call that? Partial. Yeah, you take partial derivatives, and if I put those together into a matrix, I get, the Jacobian matrix, right? So let's think about that. F, and I think I have enough time to basically explain this. F, I can think of as really, it has n outputs. And so F is really a vector of functions that have one-dimensional outputs, and they all have m inputs. Right? But n of these functions, I should say F1 to Fn are all output one number, the nth coordinate of the output here. And they're all, possibly nonlinear, of course, functions and whatnot, but they're m inputs, and each one gives you one output. And that's how I would build the whole F mapping. Okay. And now to take a derivative, I would call it BF maybe, or you would call it JF or Jacobian, depending on your Calc 3 book that you're reading. This thing would be just a matrix of all the possible partial derivatives of all of these functions. So I've got m partial derivatives of F1 and F2 and F3 and Fn. So I get a matrix, which is n rows and m columns of partial derivatives. So this matrix looks like partial derivative of F1 with respect to x1. By the way, if you see the notes, I'm going to do superscripts when we talk about manifold coordinates. So I'm going to switch here. I should have done it here with superscripts. This is a convention in, again, manifold charts that everyone uses. This is not meaning it's to a power. I'm just talking about the particular coordinate with the cubic root when I'm talking about the axis here. The F's I'm gonna have with subscripts. We'll see how this notation makes sense eventually, hopefully. Right now, just bear with me, the N functions. And I take the first partial derivative of with respect to x1. We keep going. Here I'm going to get f1 with respect to x m, f n with respect to xm. Okay, and so yeah, so I've got number of columns I've got here is m, the different variables. And number of rows I've got here is n, the number of outputs, number of 1D functions that make up my 1D outputs that make up my F mapping. Okay, so that's the Jacobian matrix for multivariate mapping. And now what we want to do is again abstract that to from the R, M, and Rn case to the manifold case. And we want to abstract it, but we also want to say, well, what the heck is it? Like intuitively, what the heck is this? Even for Euclidean space, what the heck does this Jacobian matrix do for you? Okay. Maybe I can ask the audience, what is something, why would I want to compute this Jacobian matrix? What good is it? I mean, it's if you've taken Calc 3, you've almost certainly seen a Jacobian matrix, but you also may have not actually understood why the heck you would ever want a Jacobian matrix other than to solve your Calc 3 exams. Yeah.
You do matrix multiplication with a gradient, it's equivalent to a multivariate chain rule.
Yeah, perfect. Yeah, so this, and that's excellent for our class, and we'll talk about this later because in machine learning, everything is a multivariate mapping. A neural network is a layer, every layer is a multivariate mapping from your input neuron output to your output of neurons. And there's some M inputs to the neuron and some N outputs to that neuron layer. And so every layer is one of these mappings. You have a bunch of them. And you have a gradient, you have a loss function trying to optimize, you try to do gradient ascent or descent or minimizing, sorry. You need to backprop the gradient through every layer backwards, right? And the backprop operation is multiplication of the gradient really with the transpose of this Jacobian matrix. And so it's a big chain rule to keep going back. Your derivatives gradient going back is the Jacobian matrix. So one, and we'll do this with manifolds, is gradients. Moving gradients between manifolds is through the Jacobian. Okay. And you can think of that is the gradient, again, backprop is going backwards. That's the name backprop, backwards propagation. And yes, you can do gradient back propagation across manifolds as well. One more thing, because I'm out of time, is Jacobian is going in the forward direction. What are we doing there? If I take a point, and you can think Euclidean space for that right now, don't think manifolds. If I take a point and I perturb it, that is by some vector V, the output perturbation is going to be EF times V, matrix times a vector. The Jacobians, super useful tools, not only do they back propagate gradient, they forward propagate perturbations in your input. How much will that perturb your output? Okay, again, perturbations are just infinitesimal things like tangent vectors we'll speak here manifolds. If I perturb a point in my manifold, how does it perturb in the output space will be another tangent vector. Okay, that holds for Euclid space as matrix vector multiplication. And we'll see next time I'll be able to define this for manifolds. You can do the same thing. All right, thanks everybody.
Awesome.